All right. So someone unmute themselves and tell me whether they can actually hear me or not.
I can hear you.
Okay, good. So I'm going to put this away.
Your video looks a bit delayed, though.
Say it again.
Your video looks a bit delayed.
Yeah, that's not surprising because everybody and their dog is trying to use Zoom right now. And so the university sent an email out last night saying, hey, the internet might not work very well. And I was like, no shit. So I'm on a pretty fast connection. This is probably the best I can get. That's what I want. Here we go. Okay, so you guys can mute or unmute, it doesn't matter. If you have questions, just say something because I can actually not see you right now so that I can use the whole screen for the lecture. And basically what I'm doing is I'm teaching from another classroom that I have access to that has better video set up. And so I'm going to use that. And you can see behind me, I'm just using, all I have available actually is the camera in the computer. And so I've sort of marked out on the whiteboard behind me where I can draw and you can actually see. And so that's what we're going to do. I'm recording this. So in theory, when it's done, it'll be recorded on the computer and I'll upload it to Moodle. But since this is all brand new for us, we don't know for sure exactly how this is all going to work. I've test run it and it's worked, but that doesn't mean it's going to work properly this time. Okay? And I'll be honest, like having been away for 2 weeks, I've somewhat forgotten where we were. And so what I'm going to start working on is just disk-based searching. If we've already started that, someone tell me that, yeah, we already started that. Okay, I'll assume we haven't started that. And we're off. Sorry, go ahead.
Yeah, I think where we had left off, according to my notes, is we had just been starting. Oh, sorry. I just realized that I was going early. My fault. I had read the slides the week before thinking that we were going to still have class and I was going to be gone. Sorry.
Sure.
I'm wrong. Continue where you were.
Okay, so I think we're good. But if you see this and you're like, hey, wait a minute, I saw that, tell me because that would be bad. All right. So what we're looking at now is searching data that's too large for main memory. Okay, and this is not an uncommon situation, actually. Even a moderately sized data set, no matter how much memory you have, is probably going to exceed the available memory. Okay, and so we're going to again focus on seeks as a performance metrics. Okay, because that's what we have available to us. So I'll mention right now that when we talk about sorting in memory, we know that log n is an effective sorting performance asymptotically. However, for very large n, oops, large n, even a search that runs in order log to the base 2 of n will be too slow. Okay, and the basic reason for that is that log to the base 2 of n is great, except that seeks are so slow that if you have to perform more than a few seeks, you're probably going to be running into problems. And as the data set scales in size, you're going to start running into that exact issue. And so what we're actually looking for is something that has it'll turn out logarithmic performance, but with a base of much better than 2, okay, which will significantly reduce the amount of time required to search, because it will significantly increase the size of each node in the tree from a single value and 2 children to n-1 values and n children. And then you can get much wider nodes, and if you can get wider nodes, you can get flatter trees. And if you can get flatter trees, obviously there are less levels to look through to find what you're trying to find, and less levels means fewer seeks. So that's the basic strategy here: is fatter, wider nodes, flatter trees, fewer seeks. Okay. So given these needs, we have 2 specific requirements for this base search. So the first is that it must be faster than a binary order. I'll put log to the base 2 of n here, just to be specific about the base, because we are going to get log n search, it's just not going to be log 2 of n. And the second is that collections are dynamic. So insertion and deletion must also be fast. So they must be as fast as searching. Okay? So we've seen this problem before. Like, you can get really fast search, but if the ability to build and maintain the collection is really slow, then you're not going to get any advantage from that. Okay? So are there any questions about that before I move on to some ideas? Okay. So here, don't have as many boards available to me. So we have to start thinking about, well, how are we going to do this? All right. And so there are a number of strategies that we could try to adopt. And I can take input. So does anyone have any ideas? Like, if you were sitting here thinking about this, how do you think you might try to take a crack at it? What would be a really easy way to try to take a crack at it? Silence. That's okay. So one obvious approach would be, well, let's take something that we already have and make it better so that it actually meets those requirements. So that would be an improved binary search. All right. So maybe we'll say to ourselves, well, you know what? Maybe we can make binary search meet those requirements. We just have to tweak it in some way. Okay. And so data is often stored in a binary search tree. Okay. However, BST best case performance is order log to the base 2 of n, which is too slow. That's for search, insertion, and deletion. Okay. So, and also, as data is added, BST often becomes unbalanced. So in sort of intuitive terms, it means that it doesn't maintain its balance left to right. But what it means in in practical terms, in theoretical terms, is if you go to any part of the tree, the root or any subroot, and you measure the height of the left subtree and the height of the right subtree, the difference is not 0. And it often becomes large. And so what that means is that searching one side of the tree is going to be much slower than searching the other side, which is not what you want. It's interesting. To my back and forth. I have bad posture. Okay, whatever. So there are a variety of trees that solve this, like AVL, red, black, and so on. We can think about those issues later. Let's deal first with this issue of the log2x searching, insertion, deletion problem, because if we can't even deal with that, it doesn't matter whether we have a balanced tree or not. All right. So I will just mention self-correcting BSTs. And you've seen these before. So AVL, red, black, splay trees. Use rotations on insert or delete to guarantee a certain amount of balance. Okay, so for example, the AVL tree is the tightest balance. It guarantees that the difference between left and right subtree heights at any position in the tree is no more than 1. Red-black guarantees that the difference in heights is no more than twice. So the left is no more than twice the right or vice versa. Splay trees I don't remember actually. So even though I know how to use them, which is sort of weird. But anyway. So an example is that the worst case searching on an AVL tree is 1.44 log n plus 2. That's log to the base 2. Versus log n for best case. Okay. So you can see that with an AVL tree, unlike with a BST, so BST best case is log to the base 2 of n, but worst case is n. With AVL, best case is still log to the base 2 of n, but worst case is now only 1.44 log to the base 2 of n plus 2. So in essence, it's asymptotically and it's log n performance. Okay. With some additional work to do those rotations when you do insertion deletion, but you can prove that there's only one rotation and one deletion required on any insertion to put an AVL tree that is AVL prior to that insert delete back into its AVL state. And so we get the same requirement of insert delete is no more expensive than search. Okay. So that's great, but we have to say, unfortunately, AVL is still too deep. That is, it's still giving too deep a tree for a certain number of nodes n, even if it's perfectly full, right? And so all this is telling us is that, well, we might be able to apply some AVL, red-black, splay-like operation to guarantee balance so that we can get good best case, worst case performance, but it's still not good enough. So we're going to need more than that. All right. So any questions about that before I move on? Okay. So the basic issue is, all right, we have to make too many jumps around, and every time we jump, we make a seek when we go to a new leaf in the tree. And so we've already talked about how are we going to deal with this. Well, what we're going to try to do is we're going to try to make the tree flatter, fewer levels. And the only way to make a tree flatter for a given number of values that we want to store in the tree is to try to somehow either make the nodes wider or arrange the nodes on the disk so that we can read a whole bunch of them. That is, we can cache a whole set of them in a single seek. Okay. So that's what page DSPs attempt to do. The second, the latter. So DSPs, it's a seek per node, too many seeks. We want to do the following. We want to somehow reorganize the BSP to store a set of local neighbors or local neighbor nodes on a common disk page. So in other words, we can read all of those local neighbor nodes in a single seek. They're stored contiguously on a track or a sector or a cylinder, whatever you want to call it. Okay? And so it would look something like this. So we'll draw a fairly complete tree here, not perfectly. And then I'm going to go down here. And I'll do the same thing over here. Okay, so I've only filled in the first and last ones, but you can assume that these have the same structure. And so what I'm going to try to do is I'm going to try to say something like, okay, I'm going to do this. And then there would be another page in here somewhere. Another one in here somewhere. So this is what I mean by locally neighboring nodes. Locally neighboring nodes are nodes that are all connected within a certain local distance from some root node, okay? And in this case, we're putting 1, 2, 3, 4, 5, 6, 7 nodes in each page. Obviously, in a real environment, we would have many, many, many more than that, okay? But if we can do this, then what it means is that we can read a chunk of the tree in one seek, and then internally in main memory do our operations, because a chunk of the tree will fit in main memory. And then when we go out and we pass over this boundary, we go and read the next chunk of nodes, and that also only takes a seek, okay? So we haven't actually changed the structure of the BSP. It's still a single node and 2 children, but we've arranged it on disk in a way that we can read a bunch of locally connected nodes in a single seek, okay? So here, we're storing k equals 7 nodes per page. And a fully balanced tree holds 63 nodes. And any node can be found in, at most, 2 seeks. So that's getting closer to the kind of performance we want. Okay? And we can append another page set to hold an additional 511 nodes, all found in no more than 3 seeks. Okay, and remember that, as I said, the actual size wouldn't be 7, it would be much bigger than that. So all these numbers like 63 and 511 would also be much bigger. So this is approaching the kind of performance that we're looking for, if we can make K much bigger. And so what we can actually hold in a disk page is going to be a lot more than 7, like probably a few orders of magnitude more. Okay. So I'll just put here real disk searches use K much greater than 7. Okay. So as an example, assume 8 kilobytes with 511 key value pairs. So on n equals 10 million file needs the following: log to the k plus 1 of n plus 1 equals log to the 512 of 10 million equals 2.95 seeks. Can you see that? Yeah, you can see that. Okay, so basically what that means is that if we get a standard page size of 8K and we can store 511 key value pairs inside that page, if we have a 10 million entry file, we can find any node in it no more than 3 seeks. Okay. So now we're cooking with gasoline. All right. This is the kind of performance that we want. All right. Any questions about that before I continue?
I have a quick question.
Sure.
So here, one of the biggest benefit isn't necessarily right that we've changed the structure so much as we're just taking use of what we can pull into main memory at a time, so that we're reducing seeks, but it's not so much we've changed the structure radically so that the data structure itself is giving us the performance. It's really just our understanding of how to use memory and how to pull memory into, or how to pull data into memory from disk. Is that correct?
Absolutely correct. So we've done nothing to change the structure of the actual BST, as you said. All we've done is try to be smart about how we store that structure on disk so that we can pull it in a way that allows us to grab local chunks and minimize the number of seeks to do that. And so, yeah. Go ahead. Okay. So that's exactly what was said. So this is great because we haven't made any changes to our BST. So everything we've done before will still work. The only difference is that we're going to get it into memory really fast. And when we need a chunk, we're going to grab that chunk and it's going to have all of this stuff in it that we're going to go through in main memory before we need another chunk. Okay. So that's the dream. Okay, and so now let's start talking about the reality. So there are still some issues here that we might want to think about. One is that even though we're getting good performance, we're still not particularly space efficient. Okay. So if you think about it, if we have our k equals 7 example, each page has 14 references. But so there's 6 of them point to data in the page. Okay. So there's 2 inefficiencies here. One is that for every piece of data we have 2 references. That seems inefficient. The other is that a lot of the references are directly back into the page that we've read. And so it seems like there must be a smarter way to actually do those kinds of references. Okay. So if we could represent the same data with 7 keys and 8 references, it turns out. But you notice even in this optimal case, we still have more references than values. And that seems like a waste, all right? So by their nature, BSTs are not efficient. 1/3 of every node is data, 2/3 are references, okay? And so that doesn't matter when it's in main memory, but when we start storing things on disk pages, we really want to maximize the ratio of data to references, to useless information or structured information, okay? So there are different ways that we can try to address this, but you should be able to see intuitively that what we're really saying is that maybe a node should hold more than a single value if possible. It's going to be hard to get away from the references because what the references are doing are saying if something's less than this value, something's greater than this value, this is where all of those values are stored on disk. But that might help us. All right, there are other ways like trying to break up the references and the values into different parts and so on. So there may be ways to improve efficiency, but in general, the space efficiency is not going to be great on these things. All right. A much more concerning issue is construction. So this is a much more significant problem. So we need to guarantee balance, both on initial construction and on updates. So this system will not work well if the tree is not balanced, because that means that lots of pages won't have very much in them, or we'll need a lot of pages to store all the information, in other words. And so then we're not going to get the performance that we want, okay? So here's an example, and let me actually put it all on one page so that we can see the whole thing. So we're going to insert the following into k equals 3 keys per page BSP. So CSDTA MPIB WNGURK EHOL JYQ ZFXV. I think that's the whole alphabet. I just randomized it. Okay. And so I'm going to show you the result, inserting this into a page BST, and I'm going to use an ABL strategy to do rotations to try to maintain balance. And so this is what I'm going to get. So you can see that I'm sort of flattening out the pages just to make things a little bit easier. Oops. Shit. That's a U, by the way.
This looks like a B tree, Dr. Gilly.
It does look like a B tree, and so we're moving in that direction. So what I've done is I've taken, like, there's a HDK right here, like this, and then all I've done is I've squashed it down so that I can show you the pages that have a k equals 3 value. Okay, but you're right, we're starting to look like a B tree, and that's exactly where we're going, actually. So. So maybe that helps, like, you understand, oh, okay, this looks a little good. The problem here is that not that this doesn't look like a B tree or this doesn't have some nice B tree properties. The problem is that the way we built it isn't B tree-like. So we just did basic BST with ABL rotations to get this. And so that strategy won't work for building the kinds of B trees that we want. But this is certainly the direction that we're trying to move in. Okay. Oh. What? Oh, you're exactly right. That is a B tree. I actually drew. Ignore that. I got ahead of myself. So, like what? Here we go. Okay. Okay. Da, da, da. Thanks for catching that. G E H K J L N O R Q. And there's a little F hanging off of here. All by himself. And then over here we have U, T, V, UTW, sorry. He's down here by himself. And then over here we have Y, X, Z. Okay. So that's the page BST that results when we have 3 nodes per page, ABL rotations on insertion to create the tree. So it's not perfectly balanced, but it's sort of balanced. And you can see that just by looking at it, it has a height of 4. So you're going to need at most 4 seeks to find any of the 26 values in this tree. Okay. Now, let me just talk a bit about BSTs and their variants, like splay trees, ABL trees, red black trees, and so on. And this is what we're going on here. So BSPs are built top down. This means the first few keys must go at or near the root. So even with rotations, it's hard to move them out of there, okay? And so you understand that if the first few keys that get inserted into the tree have to go near the root and they're not good at splitting the entire collection, and we don't know whether they are because in the dynamic collection we don't know what's going to follow, we're putting ourselves in a bad situation, right? So what we'd like to do is wait until we've seen what's in the tree and then pick the one that we're going to put as the root as being the median, all right? Because then we're going to get a really nice split, but we don't have that ability. So you see that CS and D are the first three nodes, or the first three values that go in, and they end up right up near the top, even with the AVL rotations that we do, okay? So in our example, CSD are the first three keys, and they're in the root page. So if you look at this, D was just a bad choice, right? Because we know this is the alphabet, so D is too close to the front of the alphabet to be a good choice for the root node. So we've got 3 values to the left and 22 values to the right, all right? And that's a function of the fact that D was one of the first entries that we put in and we're building top down, okay? So, so D is a poor choice for the root, and rotating within the page can't fix this. We must rotate between pages. So if we want to actually get D, C, and S, D and C in particular out of there, we're going to have to move them to other pages at some point. Okay, right now we're only rotating within a page. And this is very difficult and expensive, potentially. Okay, so with a regular AVL, you just walk back up the insertion path and you do rotations as required in order to put things back into place. So what's the problem when we do this with these page BSP type situations? Every time we move a node from one page to another page, first of all, that requires seeking, all right, which is an issue. Second of all, it's still non-trivial to actually keep the tree balanced when we do that. And so we can do it. It's not impossible, but it's going to be potentially expensive. And to try to find a technique that's going to allow us to do it in a way that's going to be efficient, because remember, we still need to do construction and dynamic operations like delete and insert effectively, is going to be tricky, okay? So at this point, we always have sort of a couple of choices. One choice would be that we can try to say, all right, I'm going to keep working on this. I think I can make this work. I'm going to try to figure out these problems, and then I'm going to come up with some solution that's going to give me a good result. The alternative is that you can just say, you know what, F it. This is stupid. It's not going anywhere. We need to think about this in a different way and come up with some kind of different data structure. And I don't know that you can't make this work well. I haven't actually tried because I don't care, because I have something else already that works better that someone made for me. But we're going to take the approach of like, well, you know, these are great for in memory, but you know what? For on disk, we're going to try something different. Okay. So, any questions about that before I continue? Okay. So this isn't completely wasted. So first of all, what we realized is that, oh, okay, so this very nice technique that works in memory doesn't work very well when we move to disk. We're going to see the same thing with a lot of the sorting algorithms as well. Look at that, okay, in addition to searching. The second thing is that we can actually analyze this particular technique that we've pushed to the point where we've pushed it and try and figure out, all right, what's not working? Because what's not working are the things that are going to have to work if we're going to build a new technique. So let's actually define some constraints or some goals, some requirements for the new technique, so that when we go and start working on it, we know, all right, these things we have to bake in. And so let's not build something and then at the end try to figure out is it working well or not. If we bake these things in and we build an algorithm that actually does these things, we expect that it should work well at the end, okay? So, what have we learned from this exercise that turned out to be not great? Well, we already talked about one thing, right? And that was the fact that the node at the root should be a very good value for partitioning the values that are already in the tree, okay? So the first thing we want to ask is how can we ensure keys at the root are good partitioning keys. For the current collection. And as that collection changes, obviously we're going to want to be able to change those values because different keys are now going to become the proper partitioning keys. But basically what we're saying is if we want something that's balanced, we need something that's good at partitioning evenly at the root, all right? And we need to keep that property as the tree changes in what it contains, all right? The second thing that you might have noticed is how can we avoid storing keys like D, C, and S that shouldn't be on a common page. So if D and C are on a page, we shouldn't be seeing any S's. The values that are stored in a node should be, or in a page in our case, should be relatively similar to one another. We shouldn't have this weirdo thing where we've got like a couple that are similar and one that's a huge outlier, or all three are outliers of one another or something weird like that. So that's the second property that we want to ensure. And in order to guarantee space efficiency, there's a final property that we're going to ask for, which is how can we guarantee each page holds a minimum number of nodes. So you notice that when we did our example, one of the issues we had was that we had some of these weirdo leads that only had a single value in them. And so that's fine when k equals 3, but when k equals 512, you don't want a page that only has 1 or 2 values. That's a completely space inefficient solution. And so the question is, can we dynamically construct some type of tree so that good splitting keys are at the root always? All right. If you look inside any page, the keys in there are relatively similar to one another. And so similar in the sense that they're close to one another or their spacing from one another is fairly similar? And then can we also guarantee on top of all of that, that if you look at any page, there's going to be at least a certain number of nodes on that page to make it space efficient, like about half would be good, right? And the answer is yes, with B-trees. And B-trees are these sort of amazing, wonderful structures where a single way of rethinking about how you're actually going to construct a tree allows you to do all of these things. Okay, so I think of B-trees as this really one of these ideas where you look at it and you think to yourself, man, why didn't I think of that? Because it's such a simple idea, but it produces such an elegant final result. Okay, so are there any questions before I stop here with the instruction for today?
What does the B stand for in B-tree?
Nobody knows. There's a whole bunch of different, we'll talk about that tomorrow, but there's a whole bunch of different ideas, but nobody's ever confirmed what the B actually stands for. So it's a good question. Yeah. Any other questions? All right, I don't know how many of you there because I actually haven't looked to see. I guess I could check and see how many participants are on. Oh, 12 of you. Okay, so that's not bad. It's about a class worth. If you haven't seen the email already, I did send out email about how the class is going to be restructured to try to deal with the situation that we're in now. Obviously, this is part of it. We're significantly reducing and or changing how we're going to do assignments and exams. If you go onto the Moodle website, there's a pinned discussion announcement that describes exactly how that works. If that's going to be an issue for you, get in touch with me because we can try to set up a situation for you that's going to work given the circumstances that you're under, because this is an unexpected and completely exceptional situation. Okay. And as I said before, I apologize for the fact that we have to instruct like this. Obviously, it's not as good as having you in class, certainly not for me, because I'm standing in an empty classroom talking to a computer. Obviously not for you, because you don't get to experience a lot of the university experience, I guess you would call it, that you're actually going to benefit from. Hopefully this will be solved quickly in the sense that we can start doing things the way we're expecting to do them in the fall. And if you have any questions or any concerns or anything that you want to talk about, class related or otherwise, you can always contact me either via email, or we can talk over Zoom if you want to do that. If I can't help you, I can certainly put you in touch with somebody who can. This is a stressful time, and so I understand a lot of people are very anxious about a variety of things. I'm trying to reduce the amount of anxiety that's going to come from my class. But if you feel like you need to reach out to someone, I can talk and I can put you in touch with people who are the professionals who actually know how to deal with this kind of thing. Office hours are going to be available today. I did send out a Zoom meeting. I'm going to start them at 11 instead of 9:30. I'm going to run up to BJ's because I'm always curious to see whether they've set the place on fire or whether there are people running around shooting each other. I haven't seen that yet, unfortunately, but I'm ever hopeful, I guess. Actually, I have some coupons for toilet paper. I'm sure there'll be plenty there, so I'm going to pick some up. Otherwise, any other questions that you have for me today? Also, if you have any concerns about the instruction, because it's the first time I've done this, like I wish we'd do it this way, this would be more useful, I didn't get this is not helpful, send them to me. And I will do everything I can to try to reorganize the presentation so that it's more effective for you all, because that's actually the purpose of the presentation, okay? Like I said, I'm recording this. I'm gonna find out where the recording is on the disk. I'm gonna try to get it up on Moodle. You will obviously get an email from me when that happens. And unless there's anything else, I will let you go, and I will see you again, some of you, I hope, on Wednesday morning. All right, thank you.
Thank you, Dr. Healy.
Thanks.